Welcome to this presentation on why sparse non-negative convolution is equivalent to dense non-negative convolution. My name is Nick Fischer, and this is joint work with Carl Brinkman and Vasilis Narkos. Let me start by defining a very fundamental problem in computer science, integer convolution. You're given two length n integer vectors a and b, and the task is to compute their convolution, which is also a vector, which we sometimes denote by the symbol a star b. It's defined like this. In the kth coordinate, it consists of the sum of all pairs ai times bj, where I and j add up to k. So here's a quick example. Consider, for instance, these vectors a and b, then I claim that c is their convolution. Okay, and we can quickly verify this, for instance, by having a look at this coordinate, the third coordinate in the output vector c, which should, according to the definition, be the same as 2 times 3 plus 0 times 0 plus 5 times 0 plus 1 times 1, which is indeed 7. Okay. It's very well known that this problem can be solved in time n log n via a very classical algorithm called the fast Fourier transform. And this problem and also this algorithm have a ton of applications across theoretical computer science. For instance, it's used as a subroutine in algorithms for 3-sum and all pairs shortest paths, for the subset sum problem, knapsack, and various string problems. You can also see that directly as a special case of this problem, we can compute subsets, which means given two integer sets x and y, we can compute the set of all their pairwise sums x plus y. And another viewpoint to this problem is that it's equivalent to polynomial multiplication of integer polynomials, which is, of course, one of the most fundamental problems in computer algebra. Now, in this talk, we will focus on a specific variant of this problem, which we obtain by considering two variations. First, we consider the non-negative convolution problem, which means that the input vectors a and b only have non-negative integer vectors, and as a consequence, also the output vector c only has non-negative integer vectors entries. And second, we will consider the vectors a, b, and c to be sparse, and therefore obtain the sparse convolution problem. Okay, so instead of writing down a, b, and c as an area of length n, you instead represent each vector as a list of non-zero coefficients only. Okay, so what's known about the sparse non-negative convolution problem? Having switched now to a sparse representation of the vectors, it's reasonable to not measure the running time in terms of the length of the vectors n, but rather in terms of the number of non-zero entries in a, b, and c. Let me denote this quantity by t for the rest of the talk. In other words, t is the input plus output size of the sparse non-negative convolution problem. And there has been a lot of work on finding algorithms which are near-linear in this size t. Let me mention some here. The first very fundamental breakthrough was by Cole and Hariharan in 2002, where they proved that this problem can be solved in near-linear time in t with a logarithmic overhead in n. This has been studied ever since then. For instance, there has been work on deterministic algorithms, for which you can also get an algorithm running in time near linear t, but the overhead in n is worse than polylogarithmic. You can remove the assumption that the vectors have to be non-negative. This actually works in two different approaches, for instance, using a hashing-based approach, the one which we will also see later for our algorithm, and using a very different approach by combining the best known techniques for sparse Fourier transforms and semi-equispace Fourier transforms. And finally, there has been some work on turning these log n factors into log t factors. Okay, let me just quickly mention that in order to compare all these algorithms and also our results, I'm here imposing the simplifying assumptions that we only care about constant error randomized algorithms, that the entries of all the vectors are bounded by poly n, and that the length n of the vectors is not too large in comparison to the sparsity t. Okay, now having a look at all these running times, maybe the natural question is time ordered t log t possible? You wouldn't expect better algorithms because any algorithm which is better than t log t would directly imply an improved algorithm for the dense convolution problem, which, however, is not known to be better than n log n currently. So is time t log t possible? We answer this question by yes, showing theorem 1, which says sparse non-negative convolution can be solved in randomized time ordered t log t. Okay, but maybe you're not quite convinced that this shows an equivalence of these two problems. because it could still happen that the dense convolution problem admits algorithms which are faster than n log n. But even in that case, we obtain faster algorithms for the sparse non-negative convolution problem as well. Theorem 2 says we can actually get an algorithm with this running time, d of t plus t log t squared, where d of n is the running time of dense convolutions. Okay, so theorem 2 is essentially a reduction from the sparse non-negative convolution problem to the dense convolution problem, where the running time carries over except for this error term, t log t squared. So as long as dense convolution requires at least time n log n squared, both problems indeed have the same running time. Okay, for the rest of the talk, I will try and give you a proof of theorem 1. So we will see the main ideas behind the t log t time algorithm, but there will not be enough time to cover how theorem 2 can be proven. And in fact, before we start with our algorithm, let me first outline a very typical approach to sparse recovery problems, which is called iterative recovery. For that, we assume that, unrealistically actually, we assume that there is a family of hash functions to m buckets, which satisfies these two properties. We want this family to be constant universal, which means that the probability that two distinct keys hash to the same bucket is at most a constant over m. This is in particular the behavior which you would expect from a purely random function. Next, we want this hash function to be additive, which means that the hash of x plus the hash of y is equal to the hash of x plus y, say modulo m, which is the number of buckets. Okay, with this unrealistic assumption in mind, I can now give you a quite simple and efficient algorithm for the sparse non-negative convolution problem. It's called iterative recovery, and it works like this. We maintain a vector c, which is initialized to the all zeros vector, and we repeat something until c is equal to a star b. Okay, and what we repeat is this. We're going to identify at least half of the entries of this target vector a star b minus c, and whatever we have recovered will be updated in the vector which we maintain, in c. Okay, in that way, c gets a better and better approximation of a star b until eventually c is exactly equal to a star b. So how can we implement this to do? There are three simple steps. The first is we hash the vectors a, b, and c. Okay, what does this mean? Focus, for instance, on this vector a. It gets mapped to a smaller vector of length only m by hashing every entry individually according to the hash function. Okay, so if this entry, for instance, is at position I, then it is hashed to the entry at position h of I. If two entries happen to collide under this hashing, then the entry in the hash vector becomes the sum of the two former entries. The second step is to convolve the hashed vectors of a and b. So compute this expression, h of a star h of b minus h of c. Here, for technical reasons, we're not exactly considering the same convolution which we've defined in the very beginning, but actually one with wraparound. So the star m denotes convolution with wraparound. Okay, let's try and understand this step in a picture. Here I've drawn the vectors a, b, and c on the bottom, and their corresponding hash vectors h of a, h of b, and h of c on the top. On the right-hand side, there's the target vector, which we try to recover, a star b minus c. On the top, we also have the hash of this target vector. And I claim that the relationship which is indicated by this picture is actually correct, that h of a star h of b minus h of c is indeed the same as directly taking the hash of the target vector a star b minus c. And this is true if you assume that the hash function is additive. Okay, so what we've done with steps 1 and 2 is we have computed a vector h of a star b minus c, which we will now use to recover the target vector. And how does the recovery work? I claim that we can recover all isolated buckets. By isolated, I mean a bucket which did not suffer from a collision. For instance, this blue bucket here is isolated. Say it contains an entry, 5. Then what we want to recover by recovery is we want to find the position where the 5 belongs in the vector C. Unfortunately, though, we don't know whether this is the correct position. We only know that the correct entry is 5. So where do we put this? To find out, we use a second set of vectors, which I will call the auxiliary vectors. And for A, B, and C, the auxiliary vectors are defined like this. if there is an entry where A has entry AI, then this entry is replaced by xi to the I times AI in the auxiliary vector. Here, for simplicity, you can just think of xi as a symbolic variable, which we can somehow deal with in the algorithm. Okay, now if you drag this definition through the process of hashing and convolution, of convolving, then you can actually see that the same definition carries over to this hash vector of A star B minus C. If there is an entry ck, then in the auxiliary vector, you have the entry xi to the k times ck. Now, seeing both of these entries, there is enough information available to recover the correct coordinate, the correct index k to where we have to recover ck. So we can actually know this is where ck belongs. And the very same way, you can recover all isolated buckets, which means the pink and the purple one here as well. What remains are the orange and light blue buckets, entries, which unfortunately collide under the hashing, but there's nothing much we can do here. Instead, the algorithm now iterates, and in the next iteration of this loop, we pick a fresh hash function with fresh randomness, and maybe here it now happens that these elements are split, each of which now becomes isolated, so we're able to recover the vector completely. Okay, so you can see that with this approach, as long as we can guarantee that in every step, half of the remaining entries are identified, this process eventually terminates and outputs the correct vector. And to guarantee that at every step, half of the coordinates are actually identified, we exploit the constant universality of this hash function. So you always pick M to be roughly the sparsity of A star B minus C. Okay, let's quickly analyze the running time of this process. First, it's clear that the number of iterations is bounded by log t, by what I just said before. The sparsity of A star B minus C decreases by half in every iteration. It follows that the running time can be bounded by like this. Steps 1 and 3 each run in linear time and t. They are log t iterations, so this is at most log t. But you can even bound the convolution step by time t log t. Because by what I just said before, it suffices to decrease the bucket sizes geometrically across several iterations, which means that you essentially only have to count the convolution in the very first iteration, which takes time t log t. So indeed, there is this very simple algorithm which runs in time t log t, which is what we want to prove, if we can assume this unrealistic assumption. So let's see, can we remove this maybe? What actual hash functions exist and what guarantees do they bring? There are two very popular options. The first option is this: h of x is x mod m, where m is a random prime number. Now, this hash function is additive. You can check that very easily. But unfortunately, it's not constant universal. It's just log n universal. Now, if you were to use this hash function in the algorithm, you have to increase the bucket sizes, the number of buckets by a factor of log n, which also makes the running time worse by a factor of log n. So with this hash function, iterative recovery becomes too slow. What about the second option, linear hashing? It's defined by this slightly more complicated expression. And this hash function is now very well known to be constant universal. However, unfortunately, it's not additive. It's what you maybe call almost additive, which is a property very close to additiveness, but not quite. Okay, so the difference is that this equation holds only up to an offset, which can take two possible values. Now, for most algorithms which expect an additive hash function, this error term, this offset, is not a problem. It's just a technical complication. But for this algorithm, for iterative recovery, it's actually a deal breaker. Let me give you a very vague intuition why. Whenever we hash the vector A star B minus C, what's happening due to this offset is that each entry is hashed to two buckets. However, these two buckets, the split of an entry into two buckets depends on the hash function. In particular, it's inconsistent across several iterations, which means that whenever you try to cancel out the contribution from previous iterations to make the vector A star B minus C sparser and sparser, you will actually not cancel out anything, and the vector A star B minus C stays very dense. And therefore, we cannot reduce the bucket sizes geometrically. The running time suffers again from an additional log t vector. Okay, so what's the consequence of this? Apparently, both hash functions which we know of, which have properties similar to what we expect, cannot be used for this algorithm. So iterative recovery simply is too slow and there's no way around it. Instead, what we will try to do is we will try to find an algorithm in a one-shot recovery style. So we're trying to use the same setup, hash, convolve, recover, but we lose the loop. Let's see how this looks like in detail. We do one-shot recovery from m buckets where m is chosen to be much smaller than t. We'll see why this makes sense in a second, but an immediate consequence of that is that, well, we need at least t by m many auxiliary vectors from an information theoretical argument, right? If you try to recover t pieces from information from a vector with length much less than t, then you better have many vectors available. So the picture has changed slightly from before. It's now looking like this. We still have the vectors a, b, and c, but we've introduced several auxiliary vectors. In fact, we've introduced 2 times t by m many auxiliary vectors instead of just 2 or a single auxiliary vector from before. You can see that the first vector is just the same as a, b, and c from before. The second vector, so the first auxiliary vector, is the same as the auxiliary vector from before. It's defined by this tweak xi to the I times ai in every entry. Now the jth auxiliary vector is defined similarly by xi to the j times I, xi to the j times I times ai. Maybe it doesn't make too much sense at this point why we pick the vectors in that way. So just think about the construction like this. We're trying in some sense to encode non-redundant information about A, B, and C into these vectors. Okay, here's the algorithm. Let's call it one-shot recovery. And it has the very same 3 steps. First, we hash. For that, we pick a linear hash function. Recall that this is option 2 from the previous slide. And we hash the vectors, the auxiliary vectors of A and B with this hash function. Now, for simplicity, I'm actually assuming that this function is truly additive because the almost additiveness versus additiveness issue here indeed only is a technical complication. Second, we convolve all auxiliary vectors of A and B, just in the same way as we did before. The third step gets more complicated. The goal is to recover all entries falling into light buckets, which means buckets with at most 2 times t by m many entries. Okay, recall that 2 times t by m is exactly the number of auxiliary vectors. So we try to recover all entries for which we possibly have enough information to get to do the recovery. Now, however, it's totally unclear how to do this, right? So this is what we'll talk about next. There are in fact 2 problems which we talk about next. The first one is how to implement step 3. So how to recover all entries in the light bucket. And the second one is, well, even if we can recover all entries in light buckets, then what guarantee does the algorithm give us? So can we show that all or at least almost all entries actually fall into light buckets? Okay, let's talk about the subproblem 1 first. The setup is like this. Focus on some buckets, say the ith bucket. Then we have access to all the ith coordinates of the many auxiliary vectors. If we assume that the bucket is light, then there are, say, s entries hashed to it. So each bucket is a sum of s terms where each sum is weighted differently with powers of xi. And we know that there are at least s auxiliary vectors available. Now, just by the definition of these auxiliary vectors, and if you stare through it for a little bit, you can see the following observation. The entries hashed to this bucket, ck1 through ck's, form a solution to this equation system, where on the left-hand side, we have some matrix which depends on xi. And on the right-hand side, we only have exactly the ith entries in all the hashed auxiliary vectors. Moreover, this matrix has a very special form. It's what you would call a transposed Vandermonde matrix. And for this type of matrices, it is known that you can do linear algebra faster than for arbitrary matrices. In fact, solving S by S transposed Vandermonde systems is in time S times log squared S. Now, the main reason why we can do the recovery is because we can exploit this fact. So let's see how we can apply this in the algorithm. This is the same algorithm as before, right? The first and second steps have not changed at all. The third step is unknown so far. We have to fill in this to-do. And we fill in this to-do as follows. For all light buckets, we recover the whole bucket I by solving a transposed Vandermonde system of size 2t by m. Okay, this is almost correct, except that we made a slight mistake, which is, well, we can solve these systems fast, but just to write down the system, just to pose the question, we have to know the indices K1 through Ks. Now there is an algorithm, a very old algorithm called Prony's method, which actually also inspired this whole algorithm, which allows you to recover K1, K2, and so on, if in some sense efficiently, from not significantly more information than what we have here. Unfortunately, though, Prony's method is not applicable here because it involves some algebraic computations, which are just too expensive for our purposes. Okay, for that reason, we sidestep this, this complication and instead pre-compute the support, meaning all indices k for which ck is not equal to 0, in advance. Now, I call this pre-computation, but actually this step is quite non-trivial in itself. And unfortunately, also, I don't have the time to talk more about this. It's also not exactly true that we compute the support exactly. We only compute it approximately. But if you check the details, it's still enough to make this algorithm be correct. Okay, so at this point, you should be convinced that the algorithm correctly recovers everything, every entry which falls into a light bucket. Let me also convince you that it's efficient. Okay, so the running time of this algorithm can be bounded like this. The second step needs t by m many convolutions of length m, which you can bound by t log t. The third step, and actually also the first step, require the solution of m Vandermonde systems, transpose Vandermonde systems of size t by m roughly, which you can also bound by t log t if you use the fact on the left-hand side, and if you assume that m is not too small. Okay, so the algorithm correctly recovers all entries in light buckets, and it's efficient. Let me finally convince you that almost all entries fall into light buckets, thus completing the correctness proof of this algorithm. So here's subproblem 2. The setup on the left-hand side models exactly the situation in the algorithm. We have t elements which are hashed with a linear hash function, and we'd like to bound the number of elements which fall into overfull buckets, so into buckets of size at least 2 times t by m, which is twice the expected number of elements in a bucket. So for that, we like to bound the probability p that a fixed element falls into an overfull bucket. Now, without going into the details, there is a very nice paper by Knudsen from a couple of years back, which shows that p is at most m by t times some error term. This error term, however, is too large for this algorithm. And unfortunately, you can even show that you cannot improve this error term too much. Luckily, though, we reuse parts of Knudsen's proof to show a different kind of concentration bound, to bound p by m by t times this error term n log n by t, which now depends on the dimension, on the universe size of the hash function. Okay, this actually looks worse, maybe because n is unbounded in this process, but we can anyways make use of it. Let's see how. The algorithm which I've shown you on the previous slide, the one-shot recovery algorithm, we said that it can recover all but t log t many entries if we can show that p is at most vulnerable log t, meaning that if only a log t fraction of the elements falls into overfull buckets. So all I have to convince you of is that we can bound p like this. And to make this happen, we do another pre-computation, namely a dimension reduction. So before we even run the one-shot recovery algorithm, reduce the dimension of the vectors to something small, say t log t. Then if you combine this with the theorem on the bottom left, and you pick m to be at most t over log cubed t, you get the same, you get that p is at most vulnerable log t. So the one-shot recovery algorithm correctly covers all but t over log t entries. That's not good enough, of course, because we want to recover all entries correctly. So the whole algorithm is, after this whole algorithm, we run a post-computation cleanup step to correct the remaining t log t errors, t by log t errors. Again, I don't have enough time to explain how the pre-computation and the post-computation look like, but let me finally just summarize the whole algorithm. Okay, so this is what we've seen. The one-shot recovery algorithm is efficient and it's also correct, assuming that we have done certain pre and post computations, like a dimension reduction, the support approximation, and the cleanup step. And it's actually not even true that these are the only pre-computations. You need to first do another dimension reduction to a slightly larger universe, and you need to guess the output size t to make some of these steps happen. Yeah, T, of course, is what we assume to know the whole time, but actually the algorithm is not aware of the output size T. Okay, let's stop talking about the algorithm here and let me conclude by giving you some open problems. First, is there also a T log T time algorithm with error probability 1 over polynomial in T? You can actually analyze our algorithm slightly better to get that the error probability is 2 to the minus square root log T. So the question is also error probability 1 over poly T possible? Second, is there a T log T time Las Vegas algorithm for the sparse non-negative convolution problem? This algorithm is Monte Carlo randomized, and also most of the citations from before are, so it would be very interesting to find an efficient Las Vegas algorithm. Third, is there a similar speedup for unconstrained sparse convolution? So for convolution after dropping the non-negativity assumption. I believe that this is a very hard question because almost all steps in our algorithm fail for this case. Okay, that's it. Thanks for listening.